Right, what we'll be doing right now is we'll look at a couple of examples to find the LCM and HCF together. We found out the method last time in the last two videos. And in this, we'll wrap it up with a statement to help us figure out how to find the LCM and HCF using the prime factorization method. Let's look at another method to find out the LCM and HCF. We'll look at few properties associated with LCM and HCF and wrap this video up with that. Right. Start with an example. Find the LCM and HCF of these two numbers. Start by finding out the HCF. The highest common factor. The HCF cannot contain a prime number that is not present in both the numbers. The prime numbers present in both the numbers are 2, 5 and 7. The HCF cannot contain a 13 or 17 because if it contained a 13, the second number will not be divisible by the HCF. Similarly, if it contained a 17, it cannot divide the first number. So it can only contain 2s, 5s and 7. What is the highest power of 2 that will divide both these numbers? It's going to be a 2 cube. What is the highest power of 5 that can divide both these numbers? It's a 5 power 4. And the highest power of 7 that can divide both these numbers? 7 power 1. So 2 cube into 5 power 4 into 7 is the HCF. The LCM is a multiple of both these numbers. So the LCM necessarily will have to contain 2, 5, 7 and 13 as prime factors if it has to be a multiple of the first number. And it necessarily will have to contain 2, 5, 7 and 17 as a prime factors if it has to be a multiple of the second one. So let's list all of them down. 2, 5, 7, 13 and 17. If it has to be a multiple of both these numbers, then it necessarily, what is the least power of 2 that it has to have? It needs to have a 2 power 5. If it does not have a 2 power 5 in it, it cannot be a multiple of the first number. Similarly, in the case of 5, it's going to be a 5 power 6. For 7, it's a 7 square. 13 and 17, we just list down whatever is available because they are present in only one of these two numbers. So the LCM is the product of all of these, 2 power 5 into 5 power 6 into 7 square into 13 power 6 into 17 cube. We go with one more example where instead of taking these prime numbers, we'll just generalize them with variables. If A, B, C, D, E and F are prime numbers, what will be the LCM and HCF of whatever numbers are given? This will help us consolidate the learning. To find the HCF, we'll start with the HCF. The HCF should be a factor common to both these numbers. So it can contain only those prime numbers present in both. A is present in both. B is also present in both. C, D, E, F are not prime factors that are contained in both the numbers. What is the highest power of A that can divide both these numbers? It's A power 5. Because A power 7 cannot divide the first number. What is the highest power of B that can divide both these numbers? It's a B square. B cube cannot divide both these numbers. So HCF is A power 5 into B square. LCM, if the number has to be LCM of both these things, it has to be a multiple of the first number, which means it needs to have A, B, C, D, all of these prime factors in it. If the number has to be a multiple of the second number, it needs to contain A, B, E and F as prime factors. So the LCM will have to have all of these prime factors, A, B, C, D, E, F. If it's a multiple of the first number and the second number, what's the least power of A should it contain? It should contain an A power 7 in it. Otherwise, it cannot be a multiple of the second number. The power of B will be a 3. C, D, E, Fs were present in only one of these two numbers. So let's pick them as they are available in these numbers. C square, D power 5, E power 1 and F cube. The product of all of these is going to be the LCM of these numbers. Right. Now that we have done two examples, let's basically frame two statements to tell how to find out the LCM and HCF using the prime factorization method. The prime factorization method for the HCF, we picked only the common prime factors. The highest power of any of these prime factors that will divide both the numbers is the lowest of the powers that you find in both these numbers. So how do we find the HCF? HCF is the product of common primes taken in their lowest power. Common primes of both these numbers are A and B. The lowest power of A and B are A power 5 and B square. So that's a HCF. What is it when it comes to LCM? LCM needs to contain all of these prime factors. So we are going to take all prime numbers. And what is going to be the power of the common primes? The common primes need to be present in their highest power. Otherwise, it cannot be a multiple of both the numbers. So product of all primes taken in their highest power is going to be the LCM. So for HCF, common primes, lowest power. For LCM, all primes, highest power. Right? With this, we'll move on. we'll look at the second method to find out the LCM and HCF. This is called the L division method. We'll just walk you through. If you're comfortable with the first method, stick with it. If you're comfortable with this, stick with this method. 24, 84 and 132. Pick any factor, any number that you think can divide both these numbers. Larger the value, lesser the iteration. Quickly realize that 4 divides them. 24 by 4 is a 6. 84 by 4 is a 21. 132 by 4 is a 33. 3 can divide all these numbers. So let's divide them by a 3. 6 by 3 is a 2. 21 by 3 is a 7. 33 by 3 is a 11. 2, 7, 11 are all prime numbers. So they don't have a factor in common. What is a HCF? Whatever we took as a number common. This 4 into 3 is going to be the HCF. What is the LCM? The LCM is going to be the product of all of these numbers, which is 4 into 3 into 2 into 7 into 11. 7 11s are 77 into 2, 154. 154 into 12, 150 into 12 is an 1800. 4 into 12 is a 48. So it's going to be 1848 is the LCM. Pick one of these two methods. Just stick with one. And if you feel that you're rusty about LCM and HCF, visit the essential practice section and then basically go through those 20 questions that are given there. You need to be good at finding out the LCM and HCF, and you need to find them in a really fast pace. As in, like, probably can take about 25 seconds to find the LCM and HCF of 3 numbers, not more than that. So get adequate practice. Ensure that you have mastered this. From here we'll move on. Let's look at how to find out the LCM and HCF of fractions. In the case of fractions, it's the formula. LCM of fractions is equal to LCM of the numerators divided by the HCF of the denominators. The HCF of fractions is the other way around. Find the HCF of the numerators divided by the LCM of denominators. Why does it work? What are the basis for this formula? All of these I've covered in the YY section. Before you hit the YY section to figure out how this formula is derived or why it is derived, just think about it, ponder about it. Many times if you can figure it out yourself, that gives you a lot of confidence and understanding about the basics of number properties. Right? We'll take a small example to wrap this up. We're going to pick these two numbers, 2 by 3 and 4 by 9. Let's find out the LCM and HCF of both these numbers. The LCM of both these numbers by the formula is LCM of the numerators, which is LCM of 2 and 4 divided by the HCF of the denominators, which is HCF of 3 and 9. LCM of 2 and 4 is a 4. HCF of 3 and 9 is a 3. So the LCM of these two fractions is a 4 by 3. HCF of both these fractions, HCF of the numerators, HCF of 2 and 4 divided by the LCM of the denominators, which is LCM of 3 and 9. HCF of 2 and 4 is a 2. LCM of 3 and 9 is a 9. So HCF of these two numbers is 2 by 9. Right? Get some more practice. I've given among the 20 questions, some of these are finding out LCM and HCF of fractions. Right? We'll look at few interesting properties of LCM and HCF. Right? The first one, the product of two numbers is equal to the product of the LCM and HCF of these two numbers. I'll break this into two parts. First, I'll give you a numerical example. We'll check out whether this property is actually true. And then let's look at the basis for this property. Why does it work? Let's take this 20 and 24, which we used to find out the LCM. 20 into 24, the product of these two numbers is a 480. We know that the LCM of both these numbers is 120. We computed it a little while ago. Let's quickly compute their HCF. 2 square into 5, 2 cube into 3. The only common prime is 2. In its lowest power is 2 square. So the HCF of both these numbers is equal to 4. So this is the LCM and this is the HCF. The product of 120 and 4 is also equal to 480. So 480 equals 480. So what we said as a property of LCM and HCF holds good. Hold on for a minute. This will work for two numbers. The product of two numbers is always equal to the product of the LCM and HCF of two numbers. For more than two numbers, right? More than two numbers, this may or may not hold good. So please do not extrapolate it thinking that product of three numbers is going to be the same as the product of the LCM and HCF of these three numbers. It need not hold good. Let's look at why it works. We'll prime factorize 20, which is a 2 square into 5. Prime factorize 24, which is equal to a 2 cube into a 3. Right? I'll just name them as A, B, C, D. The product of all of these four is what resulted in a 480 for us. Now, what did this LCM contain? The LCM contained all the prime factors. So it has a 2, 3 and 5. It picked these in their highest power. So it contained a 2 cube, 3 and a 5. So what all did we get here? We got a C, we got a D and we got a B here. What does the HCF contain? It contains only prime factor that's common to both these numbers. 2 is the only prime factor common to both. In its lowest power is 2 square. So what have we got here? We got an A here. So A into B into C into D was our left hand side. The right hand side is C into D into B into A. Commutative property of multiplication. Both these should be equal, which is why it works. In terms of if I put it in words, the LCM takes all prime factors that are there in their highest power. The HCF takes only common prime factors. So if there's a common prime factor, it will be present in both the numbers. The highest power went to the LCM, the lowest power went to the HCF. So we accounted for both. If it's not a common prime factor, it will be a part of only the LCM. So which is why this method works. Let's move on to the second property. Second one is, if two numbers do not have any factor in common, they have no factor in common, they are said to be relatively prime or co-prime numbers. They have no factor in common and they are integers. One is definitely going to be a factor of them. Essentially, co-prime numbers are those whose HCF is equal to 1. Let's relate it with the previous property. The last property was, there are two numbers A and B. The product of A and B will be equal to the LCM of AB into the HCF of AB. If A and B ended up being co-prime numbers, the HCF is going to be 1. So the LCM of these two numbers is going to be equal to the product of the two numbers. Let's dig a little deeper into this co-prime numbers, understand some more properties. Two prime numbers will always be co-prime. Obviously, definition of a prime number is they have only two factors. One is 1 and one is the other number. So 3 and 5, can they have any factor in common? Cannot. So they will be co-prime. Is it only prime numbers that will be co-prime? Not necessary. A prime and a composite may, understand this modal verb, it's may be co-prime. Look at an example, 3 and let's say something like 16. 16 is a co-prime number. The factors of 16 are 1, 2, 4, 8, 16. None of this is common with 3. So these two numbers are co-prime to each other. Can two composite numbers be co-prime? Certainly. Here is an example. Take 9 and 25. Factors of 9 are 1, 3, 9. Factors of 25 are 1, 5, 25. No factor in common. So they also may be co-prime. One other interesting thing. Two or more consecutive integers will always be co-prime. Why? Let's have a look at it. Let's take it 25 and 26. Is there any factor common to them? 1, 5, 25. 1, 2, 13, 26. Nothing. Take 100, 99. Any factor in common? For 99 it's 1, 3, 9, 11, 33, 99. For 100 it is 1, 2, 5, 10, 25, 4, all of these. But there's no factor in common. Why does it work the way it works? Pause the video. Think about it for a minute before you hit the play button to check out why it's working. Let's say x is a factor of 25, which means x will perfectly divide 25. When x divides 26, the remainder is going to be equal to 1. Take any two consecutive numbers. If x is a factor of one of the numbers, it will either leave a remainder which is -1 or +1 when it divides the other number. So essentially, two consecutive numbers will have only one factor in common that's going to be equal to 1. Two or more odd consecutive positive integers will also be co-prime to each other. Move on further. The last property in LCM HCF that we're looking at is this. For any two numbers, the LCM is always a multiple of the HCF. Pause the video. Think about this statement. Pick an example. Check out how it works. And then come back to the video to check out whether what you have figured out is the same as what I'm saying. Here is the logic. Let the LCM and HCF of these two numbers be L and H. And let the numbers be A and B. If H is the HCF of both these numbers, then H has to be a factor of both A and B. If L is the LCM of A and B, then A and B will both be factors of L. Which essentially means that H has to be a factor of L. It's like this. H is a factor of A and B. A and B are factors of the LCM. Which means the HCF has to be a factor of the LCM. I will leave you with one question. If the product of two numbers is 96, can their LCM and HCF be 16 and 6? Whew. We covered quite a bit in this video. It's a lot of concepts to cover in one single video. Time you took a break. Use the break for two things. One, subscribe to this channel. And two, sign up for the most comprehensive and affordable GMAT quant course that's available online at gmat.visaco.com.